Okay, now it's recording. So if we take a look at this handout, the course information, I'll just give you a brief rundown. If you have any questions, feel free to interrupt me anytime. But this is just part 2 of General Chemistry, the year-long series. And so here's the course description. Really, when we break down the course, we're going to be spending more than half on one type of concept. No, that's not the right word. On just one concept, basically. And it's equilibrium. Equilibrium, in particular, associated with chemical reactions. And you probably know, you may know a little bit about equilibrium. Equilibrium happens when you have like a weak acid. A weak acid partially ionizes. So if you have partial reaction, how do you predict the stoichiometry of that reaction? You know, so for example, if you have acetic acid and it partially ionizes, well, what percentage of the acetic acid molecules actually ionize? Is it just a simple fixed percentage, or how do we handle that? And so we're going to focus a lot of our time this semester on trying to predict, you know, the stoichiometry of these partial reactions, i.e. equilibrium, and doing equilibrium calculations instead of your straight stoichiometry. You know, in Chem 1A, you do stoichiometry, you just predict 100% reaction. You know, it's going to go, whatever the limiting reagent is, you know, that's how much you're going to produce, right? In Chem 1B, it's a little more complicated because not all reactions go all the way, and so we'll spend a lot of time. But that said, if we look at the course description, you know, chemical equilibrium should be, you know, quite a bit bigger because that's the major topic of Chem 1B. Thermodynamics is also important, kinetics. Transition metal complexes, less, you know. And so this is lopsided towards chemical equilibrium, but maybe I should do like an infographic or something like that to show that. In the lab, we're going to be dealing with a lot of chemical reactions in the lab as well. All right, the course objective, you can read through that. We have SLOs for this class, 2 of which are written here. You know, the first one is by, the first one is for predicting chemical reactions. The second one is for goggles. All right. And of course, there are plenty of other learning objectives in the course. A prerequisite is Chemistry 1A. Okay, and then the book we're going to use is just the 10th edition, Volume 2. The 11th edition's already out. We'll continue with the 10th. The lab manual is a self or custom published booklet. This is kind of pricey. I think it was how much is it? $27? Did anybody purchase it yet?
I think it's 28.
Okay, $28. All right, so you'll need Volume 2, a Petrucci, Catalyst, a composition notebook like this. I'd like it, you know, with the graph paper rule, quad rule. You know. You could write on both sides or on one side, but this is an example of it. Actually, this is an example of not a lab notebook. This person did all their homework. This is their homework notebook here. I should have brought in one for the lab. But you can get another for your homework if you'd like. Safety goggles, the ones you had from Chem 1A are fine. A scientific calculator. My recommendation for a scientific calculator is do one that can solve quadratic equations. You know, you'll use the basic one. It's not like the $10, $11 calculator. It would be like the $15, $16, $17 calculator. And that calculator, it's still approved for the SAT, but it solves the quadratic equation. In solving these, you know, equilibrium calculations, these partial reactions, stoichiometry, we have to do the quadratic quite a lot, and it becomes tedious. And so if you have a calculator that you can just plug in A, B, and C, and get the X value, it makes life much easier. And so I recommend that, and you could go take a look. My particular calculator is the Casio, FX115, but EX. You can get whatever you want. But I got mine at Target. But they sell it. I've gotten a lot of these because I seem to lose them, and so I purchased this I think at CVS, Target, etc. And so I think it's a Casio FX115 ES. Right now my calculator is missing. Mm-hmm. Yeah, that's it right there. You can hold it up. Thanks. How much did you pay for that?
I think it was $11.
$11? Oh,
Walmart.
that's good. Walmart? Okay, Walmart. Yeah, that's great. So check that out. It's a good deal, and it's a really good calculator actually. Very good. But TI does make one, and other manufacturers too. So you don't have to buy any particular brand. You'll want a Sharpie pen for lab. Although I'll have some extras usually, so. But if you don't want to share, sometimes you have to wait. Get your own. For lab, a lab coat is good, or a lab apron. Helps protect your clothing as well as yourself from spills. Lab coats are now required. Like at Santa Monica College, they require everybody to wear a lab coat. UCLA. The last lab coat I purchased was off Amazon, and I spent like $26, I think, a white lab coat. They can get expensive. Long before that, I bought a cotton one, which was like $80. But this one, the $26 one's fine. Gloves. They also require gloves at UCLA, because of some accidents that have happened here. And I recommend gloves. I used to use latex gloves, but latex gloves don't breathe. Nitrile gloves breathe a lot more, and so I recommend nitrile gloves. Not only do they breathe more, but they're less permeable to a lot of chemicals. Nitrile gloves have much greater chemical resistance than latex, that's for sure. And so they're just overall much better material. Okay, so I recommend those, and you can buy those everywhere. They sell them. All right, let's flip the page over. You're required to attend both lecture and lab, especially lab. Lecture, okay. It's good. Of course, it's good to attend. I never missed a lecture. If I could help it, I would never miss a lecture. But some people do miss them, and that's all right. That's not going to influence your grade. But if you miss lab, that's a problem. That will impact your grade. And so make a point of making it to all the labs. Okay? If you do happen to miss a lab, you'll need to make it up to get the points back from that. Makeup, we have to work, on a case-by-case basis. So just don't lose those points there. Okay, exams though. If you miss an exam, that's a bit more complicated because it can carry up to a grade drop, like 10% penalty. Depends on of course, depends on the scenario, circumstances. Okay. Approximate grade distribution. The exams and quizzes are going to be worth about 500, approximately. This will change as the semester goes along. The exams, these quizzes are very short, like 5-minute quizzes. The exams are a little longer, like an hour and a half, the test. We're going to have a lot of exams this semester, so I'll tell you more about that. Actually, since we're on that, if you could just take a look at the next handout, which is the syllabus. And if you try to look for the exams on here, you aren't going to find them. And the reason is because for Chem 1B, what I do is I don't give like 4 exams or midterm or whatever. I give chapter exams. So what we'll do is we'll have a test on each chapter. So when we finish a chapter, then you'll have about a week to prepare for the exam, and then you'll take it. And so I made the lab schedule a little flexible. Most of the exams are going to happen on a Thursday. Sometimes I'll have it on a Tuesday, but they'll definitely be on a lab day, and you'll be warned in advance, when the tests are going to be. And so the way this is going to work is, okay, we're going to do chemical reactions, let's say this week, and then you'll have a test, say next week. So your first test will be next week. We'll do chapter 15 next week, and then you'll have an exam on chapter 15 following week. Chapter 15 looks like we're only covering it one day, but it's probably going to spread from Thursday through Wednesday a little bit. This is the overlap. Any questions about how the exams work? All right.
Yeah, how do you set them up? Do you have multiple choice for response? How do you typically?
Oh, yeah, there's going to be a mix of multiple choice. The first part, the tests are only 2 pages long. And so on the first page, you'll have some multiple choice. Actually, what I'll do is I'll just kind of compress it into 1 page. And so you'll have some multiple choice and some free responses. It's pretty short, 20 questions or something. What I'll do is I'll post last semester's tests on Piazza. You can see, the format and get a feel for what's expected. Okay. All right, the next item here is homework. This is why this person had a homework notebook. They did all their homework, and then I just check it off. What I'm looking for when I check the homework is I'm not searching for the right answer. I'm not going to check every single question and see if you have the right answer. And in fact, it's a waste of time to do that because you can do it yourself. The complete solutions manual is available, right, for the book. So in fact, so all I'm going to look for is that you attempted and gave it a serious attempt, although it should be complete. And so with that kind of homework policy, and there's some debate about this amongst instructors. A lot of instructors really don't think what I'm doing is a good idea, and that is, you could literally just copy down the answer from the solutions manual and get 100%. Well, that's what I want you to do. If you get, for the homework, I don't want you to spend like hours on one problem. If you're spending hours on one problem, then just leave it and go on. I never really, if that problem is not clicking, and let's say you're banging your head on the wall because something is not sinking in, then come back to it because you spend a little bit of time thinking about it, a little bit like. I don't mean seconds, but I mean like 5 minutes or something on it. See if you can figure it out. But if it's not clicking, then move on. And then usually what happens is you see a lot of problems, and then your brain, even though you're moving on, your brain's not moving on. And this is something like when I transferred to UCLA. I was trying to figure out, the best techniques for studying and all this other stuff, right? But I'd had many experiences at UCLA where, I'd be working on a final exam, and there's one question that stumped me, And usually the tests are like that. At UCLA, let me tell you another difference between this. And at UCLA, the tests are written hard so that the percentages are low. Like no one gets a high percent. Usually the average is like 60, 50%, sometimes 40%, right? Because they put in too many problems and hard ones. So you can't finish the exam. Basically, you have to pick the problems you want to solve and do those, right? That's one of the test strategies that I found. Not all classes are like that, but I'd say a good proportion of the ones I took. And so I finished a final exam, and there was one question that was bugging me, but it was too late. I wasn't able to get it. And then afterwards, I went down to the Ralph's, and I was waiting in the checkout line, and then all of a sudden it hit me. I mean, it's so easy because it just goes to show that your brain is still trying to make the connections between that. And so try to come back to it, and if that still doesn't work, you got to think about time, because you don't want to spend all your time in Chem 1B just studying one problem. You need to have a wide breadth of problem-solving ability. The way you get a wide breadth is you do a wide variety of problems. Okay, and so if what I don't want to see is I don't want to see blank. I don't want to see a whole bunch of blank questions because they stumped you. If they stump you and they keep stumping you, then write down the answer, because then your brain is going to start making those connections, and then in the future, when you have new problems to solve, at least that's registered. And so write down this complete solution in there. And therefore, everybody should get 100%. But I say everybody should get 100%, but nobody ever gets 100%. Not nobody. Let me rephrase that. I expect 100% on the homework, but you would be surprised. I don't. It's just a small percentage of the class that gets 100% on the homework. Everybody else, they leave a lot of blank. It has to do with a lot of things, time, whatever else, constraints. But those are give me points. When you get give me points, you got to take advantage of those fully. So there's also kind of a severe penalty on the homework, which is 50% late penalty for the homework. But the late penalty, when is the homework due? The homework is going to be due on the day of the test. And so if we're having a test on chapter 15, the homework will be due at the beginning of the test, beginning of the class. And so chapter 15 homework will be due on the chapter 15 exam day, which is likely September 15th. Chemical reactions review homework will be likely due on September 8th. We'll see. The schedule is a little bit flexible, depending on how things go. All right, the labs carry a much more severe penalty. No late labs are going to be accepted this semester. But the lab due dates are this. The labs are going to be due a week after we complete the experiment. This is for the simple labs. There are a number of labs that are more complex, like qualitative analysis. You'll have more time to complete that. The synthesis lab. The synthesis lab is not just a simple report sheet. We're going to do a formal scientific report for that one, and so you'll have a lot more time. And so there are a few labs that you'll have a lot more time than 1 week, but typically the labs will be due a week after. The final exam is going to be a comprehensive final, and it's going to be worth 20% of your grade. So if our point total doesn't add up to 1,000 points, then it'll be 20% of whatever our point total is. So I don't over-bias it. The grades are going to be 88% will be the cutoff for an A, 78% for B, 65% for C. This is the lab policy is the same as Chem 1A. If you fail lab, you're going to fail the course, even if you're getting an A in the course. A note on cheating: academic honesty is mandatory. If you have any special needs or requests, make sure you consult with the Special Resources Center. You have a testing center there. You can work with them as well. Let me know how soon. All right, any changes to the course, I'll try to notify you on this website, piazza.com. And so I saw a number of people have already signed up for Piazza. It's great. That's usually where I'm going to post things, so let me just show you what it looks like here. thing starts up. All right, and we'll let this start up, and then the definition of chemistry. So are there any questions on the course? Is there anybody trying to add the course? Just two? All right, let me see tomorrow, about that. So if you come tomorrow also, get me set up. All right, so if you're trying to add the course, obviously you didn't get the email that was sent out, but I sent out an email invitation to all the registered students in the course here. And this is the all right, I put the handouts here in case. But this is where I'll post the old test, like I mentioned, if you want to see that. Also, I put some stuff for chemical reactions here, and some stuff for the lab. The videos, the recordings for the lecture, I'm going to post on Chemistry ECC YouTube. All right, so if you want to sign up and you didn't get an invitation, then you'll need an access code. I think my class might be the only chem class there, so it's pretty straightforward to find it. Or just chem, for sure the only Chem 1B class there. The access code is just Chem 1B. This is for Piazza. The other nice thing is this. For Piazza, it's not just me that can post stuff, but you can too. And so if you have any questions, you can just put it there, and other students can answer them. Feel free to answer anybody's question on here, or I'll get to it when I see it. Okay. So go ahead and take advantage of that. Okay, if you do have questions, I also do have office hours. And my office hours are either going to be in this room, after class, or Chem 108, which is right across the hallway, it's the computer lab, or Chem 120, which is my official office, or Chem 160, it's our lab, Chem 162, our lab. And so I'll be in one of those rooms. And the office hours are on the syllabus here and also on the course information sheet. All right. Well, let's get into this. I'm not going to take roll today. I'm just going to use those sheets. Plus, I'm going to have you do a little thing for the scientific method. What is the scientific method? This is one of our SLOs, student learning outcomes. And so, at least maybe you can tell me the steps in the scientific method. What are the steps of the scientific method, or what is the scientific method?
Developing and forming hypotheses about a particular topic or method.
Yeah, okay, that sounds good. A hypothesis is definitely a key part of the scientific method. And what would the definition for hypotheses be? What exactly is a hypothesis?
A prediction as to how an experiment is going to result.
A prediction as to how an experiment will result? Okay. good, except, the thing I'm going to do is I'm going to change it a little bit maybe, as far as the scientific method goes. As far as the scientific method goes, is this. When I think of the scientific method, I think of a certain number of steps. What scientists are good at is they're good at observing nature. When scientists want to observe nature, take detailed measurements, And when they observe nature, sometimes they start to see patterns or trends. And so they're looking for some kind of order, in nature, right? And then from these patterns and trends, if they're reproducible, you always see the same pattern. Like, so for example, if you compress a gas, what happens to the volume? So let's say we went from 1 atmosphere to 2 atmospheres. What's going to happen to the volume? It's going to shrink, and the volume's going to shrink by half, right? And does that always happen? Yeah, it seems to always happen. And then, if these patterns and trends seem to always occur the same way, we can call it a law, a scientific law. But a scientific law, what exactly is a scientific law? A scientific law is usually some kind of mathematical equation that fits, the pattern. A mathematical equation is a very concise definition. And so a law would be like the ideal gas law, PV equals nRT, right? And where does PV equals nRT come from? It comes from people observing gases. I'm going to compress it, what happens to the volume? I'm going to decrease the pressure, what happens to the volume? Increase the temperature, what happens to the volume? All this stuff is just from observations, and then you take all those observations and you try to come up with the most concise definition possible, and that most concise definition is PV equals nRT, right? Or when people take very accurate measurements, they see, there's some deviations, so they might come up with another law, like the van der Waals equations. You guys remember the van der Waals equation? So it's a little bit of a modified version of the ideal gas law. And so we have a scientific law, but is the scientific law, the ultimate? Are we done now? We have PV equals nRT. Are we done? No. We could use laws. We use laws all the time to make predictions, right? We predict what's going to happen to the gas under other scenarios. But the laws does that really give us a good fundamental understanding of chemistry? If we have this, actually, if you think about PV equals nRT, you don't have to understand anything about chemistry, right? You just plug in some numbers and you get out the answer. And so, like an elementary school child learning algebra could figure it out. You have one unknown, and now they're doing that. Solve for that unknown, X. And so scientific law, that's great. And we usually, these are typically empirical laws. Have you ever heard of empirical? What does empirical mean?
It's proven objectively.
Proven objectively? It's proven objectively by observation. So empirical, when I think of empirical, what these are based on observation. And what are observations? Observations are scientific facts, right? I mean, it's a fact that this pen will, drop down to the counter. That's observation, right? And so Newton would go in and he'd look at, what's the velocity when it hits and how long did it take, and then he came up with Newton's laws of motion, right? Newton's laws of motion, those physics laws are empirical equations. Empirical equations are mathematical equations that are based on observation. Did Newton start off with, there's something called gravity, and then I'm going to derive the theory, not the theory, I'm going to derive my laws of motion based on the theory of gravity. Is that how it worked? No, it didn't work like that. You know, Newton took these empirical observations and then came up with these empirical equations, these mathematical equations. So we have the law, okay, and then we got to think, you know, well, are you Chem 1B? Okay, there's some seats up here. There's some handouts over there. But we have some equations. We can use those equations to do a lot of things. Like, for example, you use ideal gas law to make all kinds of predictions. You use Newton's laws of motion, right, to predict how long, how fast, etc. But there's something missing, and that something that was missing for Newton is, you know, what's causing, you know, or at least this pen to drop, let's say. And so then he came up with some hypothesis. You know, this hypothesis was that there's something called gravity, and there's this, you know, force of attraction between two bodies, right? That's a hypothesis. And so what the hypothesis is what we call a fundamental explanation of the phenomena. And so hypothesis is the fundamental description of the, you know, of the observations. And so we have lots of cases, you know, from Chem 1A of the scientific method. So, for example, you know, when you burn a candle, the candle loses mass, but did the mass change in? Yeah, the candle loses mass, but the total mass did not change because the candle was converted into CO2 and water, and that CO2 and water, when you add up the mass of that, it's the same as the candle and the O2 that went into it. And so we have like the you know, observation that the mass of the reactants is equal to the mass of the products, which we call the law of conservation of mass. It's a pattern and trend that's observed for over and over and over, right? And then we come up with the law of conservation of mass. Okay, then we got to come up with a hypothesis. Why is mass conserved? You know, why doesn't some mass disappear and some mass is gained? And so what was the hypothesis for the law of conservation of matter, or mass?
Nothing be created or destroyed.
Yeah, it can be, neither created nor destroyed. Matter, right? But, you know, okay, it can neither be created nor destroyed, but why is it changing? You know, it changed from a candle to CO2, you know, O2, and water. You know, why is that? And so we needed a little bit more. Yeah, okay, that's true. It can neither be created nor destroyed. That's one of the parts of the hypothesis. But, you know, to give a more fundamental description of what's happening, you know, then the hypothesis for that, the law of conservation of matter, was that matter, you know, exists as atoms, and versus, you know, ether or whatever else. And based on the rearrangement of these atoms, you know, the atoms can neither be created nor destroyed, but they can be rearranged. And so the atoms get rearranged, and this is why we end up with the products, and the products have the same mass as the reactants. That's the fundamental description, you know, that matter consists of atoms. And if enough people accept that, then it becomes a theory. And so something like the law of conservation of matter ended up giving us atomic theory, you know, that matter consists of atoms, right? You know, the pen dropping, or the apple dropping on Newton's head, gave us the theory of gravity, because he's thinking, why is that apple dropping on, you know, down to the ground or wherever? And so the theory is, okay, so what's the difference? Well, both of these are fundamental descriptions. So the key difference between a theory and a hypothesis is this. You know, it's a fundamental description of observation. But a hypothesis is what we call a tentative. Whereas a theory is a widely accepted. just because it's widely accepted doesn't mean that it's correct, right? Can you give me an example of a theory that might have seen wide acceptance that was either modified or abandoned?
The geocentric theory.
Okay, geocentric theory. Are you a geologist or no? Okay. How about from Chem 1A? Give me a theory from Chem 1A that was modified or abandoned.
Atomic orbitals.
Atomic orbitals, yeah, the Bohr model or the Bohr theory. That's one. You know, the Bohr theory, where did it start off with? It started off with observations of a strange hydrogen atomic spectrum, you know, with the lines. And then the mathematical pattern, you know, you have the, what do they call that equation? They called it it depends on how it's arranged. If you're solving for energy, they call it this. If you're solving for wavelength, they call it this. If you're solving for frequency, they call it this. I think the equation, they're solving for frequency, and they called it what? What was that equation? Do you know what the equation? I think. Well, I usually solve it for energy, but the equation I'm thinking is, you know, delta E or E is equal to, you know, this R sub H. You know R sub H, where that came from? It came from the guy's name for that theory. The guy's name. R sub H. 1 over n squared final. Do you remember this equation? 1 over n squared initial. I know summer and chemistry. I'll tell you, you know, if you took, I assume most of you took Chem 1A, you know, last year, right? Last academic year. Actually, how many people took it over the summer? Okay, a couple. Well, that's good, because in the summer you'll still have some of that information fresh in your mind. You know, let me go on a tangent, a short tangent here. Think about how much stuff you forgot from Chem 1A over the summer. Lots, right? And so this always happens. So, you know, I being a chemistry major, and I have friends who are bio majors. One of my bio major friends is going to take the MCAT. You know, he's a senior at UCLA. I was at UCLA too at that time. So he asked me for help. Can I help him with the chemistry? Because at the time the MCAT consisted of a lot of general chem. So I said, sure, I'll help you. And so I sat down and started working with him through the stuff. But I realized he forgot everything. Everything. I mean, there's no way he was going to be able to take the MCAT the next round. And it turns out there was no way. I mean, he forgot everything. He had to start over again, basically. And he ended up taking, well, he took it numerous times, but in total, he ended up taking like 4 years off to work and review. Basically, going back. Obviously, it's easier, you know, the second time around. It doesn't take as much time, but just think about that. You know, it's easy to forget, and after a few years, it's gone. Continuing on this tangent, this is one of the things I did at UCLA. I changed the way I studied for the final. You know, when I was at UCLA, normally I just start preparing for the final before the final, right? But I found that was causing me too much stress. You know, as a final, they have a finals week. During finals week, I was getting too much stress studying for the finals. And even though there were no classes, here it might be even more stressful because you don't have a separate finals week. You know? And so I did just something simple. You know, I remembered my friend studying for the MCAT. I remembered how easy it is to lose that memory. Well, actually, no, this was before. Sorry, I'm getting mixed up. But anyway, what I did was this. I just started studying for the final every week. And so what I do is, and this is what, because my memory isn't so great, what I do is I just took down notes, you know, and then I just made sure all my notes were complete and accurate. And then I just study from the notes. Before, I would try to go back and reread the book. But I took an engineering class at UCLA. The book was 1,000 pages long. You know, a 1,000-page long book. There's no way you're going to go back through that book. It's just going to take way too much time. And so, if you have a complete set of notes, you know, how long does it take to go and reread 1 week's worth of notes? No time at all. And so by the time you get to the 15th week, you've read through the first week so many times, it's like ingrained in your memory. And then all the other weeks, you know, you just keep rereading your notes. That's it. And then that decreased my stress level by, I don't know, 90%. It made the final exams much easier, too. But let's go back to this. I was talking about here. So the Bohr theory was eventually abandoned and actually not completely abandoned. Some of the aspects were retained and replaced with what theory? What was the theory that replaced the Bohr theory?
Quantum mechanics.
Quantum mechanics. And quantum mechanics is the current modern day theory, pretty much underlying chemistry. Chemistry is all quantum mechanics. Quantum mechanics are these electrical interactions, orbitals, that kind of stuff. Not orbits. You know, Bohr dealt with orbits. What's the difference between an orbit and an orbital? Huge difference, right? So you should know that. But one of the things that a theory must do is, 1, it must be widely accepted, and 2, it must be able to predict new, unforeseen, spelling. My spelling's weak, so forgive me. Predict new, unforeseen observations, phenomena, etc. All right, so let's take a step back and look at atomic theory. You know, what was atomic theory able to predict? Well, this is way back at the beginning of Chem 1A, but atomic theory was able to predict the law of multiple proportions. Do you remember the law of multiple proportions? That it's going to be CO2, not CO2.1 or CO2 point whatever, 1358, you know? That it's going to come in simple whole number ratios. That was a prediction made by Dalton's atomic theory way back when. And so Bohr, you know, well, what are we going to do with the Bohr theory? The Bohr theory should be able to predict the spectral lines of the other elements, like helium. And so you move on from hydrogen to helium, and the Bohr theory completely failed to make the prediction of where the line should be in the spectrum. And therefore, the Bohr theory was wrong. It's not a theory. It could not predict even the spectrum for the next simplest atom, which is helium. Quantum has been very successful. Quantum's been able to predict many things, you know, including one very famous prediction quantum made was this thing called nuclear magnetic resonance. Based on quantum mechanics, they predicted that, you know, atoms with magnetic moments should act like little magnets in an external magnetic field, and from that came things like the MRI. You know, the MRI was just a prediction from quantum mechanics, you know, initially. All right, so this is basically it. But you know, where are we? Well, you know, sometimes we just use the law, like the ideal gas law. Did you really think about, you know, what's happening with the gas? Well, probably, because then the theory. What was the theory? Was associated with this is kinetic molecular theory, right? Gas consists of little particles, that kind of stuff. Or you just use the law itself. And so there are many cases where, you know, this gets more and more complex, so we just base things on, you know, our observations, just these patterns or trends. Even patterns and trends are useful. And so that brings us to the first part of this, but before we get to the first part, which is chemical reactions, we're going to do a little exercise in patterns and trends, just to review a little bit. Erase this here. And so let's look at, you know, carbon, and what comes after carbon? Going left to right. Nitrogen, and then oxygen, fluorine. And then we'll look at what's under nitrogen. Phosphorus, and sulfur, chlorine. All right. Do you know what's the formula for the carbonate ion? This is just some observations we'll take. What's the carbonate ion's formula? Uh-huh. CO3 2 minus. That's good. So this is carbonate. CO3 2 minus. All right. This is observations with 8 anions. And so this is what I want you to do. I want you to fill out the rest of this here with the 8s. You can work with a partner. I want you to turn this in though too. So if you work with a partner or your neighbors or whatever, just turn in one sheet and write all your names on it. Okay. But go ahead and fill this out for me.